Lesson 4.6. Perform operations with complex numbers. When you were young, you learned to count. 1, 2, 3, 4, 5. Then as you got older, you learned to operate with combining those counting numbers. Learned that 1 plus 2 equals 3. Next, you learned about negative numbers and fractions, and more rules for operations. Finally, today we're going to learn about complex numbers and the rules for dealing with them. Complex numbers can include imaginary numbers, imaginary units. The imaginary unit is I. I equals the square root of negative 1. So you think, well, what times what makes negative 1? Can't take a square root of that. Well, it turns out that I squared is negative 1. So the square root of negative 1 must be I. Alright, so let's simplify this. Square root of negative 9. Well, that's the same as the square root of negative 1, and it's times the square root of 9. Square root of 9 is 3, and the square root of negative 1 is I. So it's 3I. Let's try another. We can split this up into, well, the 12 is 4 times 3, and we have the negative 1. So it'll be the square root of 4, square root of 3, square root of negative 1. That gives me negative 12 if I multiply it together. Square root of 4 is 2. Square root of 3 I can't simplify. Square root of negative 1 is I. And if you're wondering, yes, I usually goes at the end. We can graph complex numbers. Complex numbers include real numbers and imaginary numbers. So overall, we have complex numbers. We usually deal with just the real numbers. Imaginary numbers are going to be any number with I, our imaginary unit. We write complex numbers a plus bi, where a and b are real numbers. We can graph them. We have what's called the complex plane. It looks like your regular xy graph plane, except for the x-axis is the real numbers, and the y-axis is the imaginary numbers. So, if I graph negative 4 minus I, that's negative 4 in the real and negative 1 in the i's. Or how about 5? That's 5 in the real and 0 in the i's. So it just stays right there on the axis. Or 1 plus 3i. That's 1 in the real and 3 in the I. To add and subtract complex numbers, you do it the same way as we do with x's. I mean, I is just a letter. So you add like you would with any letters. You combine like terms. So let's add these two complex numbers. So let's add the numbers without the i's, so the negative 1 and the 3, and the numbers with the i's, 2i and 3i, which gives us 2 plus 5i. Let's try this one. Have the numbers without I, so it's 2 minus 3, which is negative 1, and negative 3i minus a negative 7i, negative 3i minus a negative 7i. So that'll give us negative 1 plus 4i. Oh, here's a longer one. Same idea. You'll deal with the numbers without the I, so I have a minus 3 plus 2. And then with the i's, I have 2i minus I plus a negative 3i. So it gives us negative 1 plus or minus 2i. To multiply complex numbers, it's just foiling the distributive property. Just remember, I squared is negative 1. So everywhere where you get an I squared, turn it into negative 1. So to multiply this, it's just the distributive property. Do the I times each of those. So we've got negative 3i and negative I squared. Oh, but wait, I squared is negative 1. So this turns into 1 minus 3i. Let's try another. Okay, let's FOIL. So we have our first, gives us negative 12. Outers, gives us negative 4i. Inners, negative 18i. And last, negative 6i squared. Combine like terms, remember, I squared is negative 1. So negative 6 times negative 1 gives us 6. Combine like terms, we get negative 6 minus 22i. Here's another. Let's multiply these together. So you have first, outers, inners, last. So the first are 1 times 1. Outers are 1 times negative 2. Then 2i times 1. And 2i times negative 2i. Combine like terms. Those are going to add up to 0. And I squared is negative 1. So it looks like we have 1 plus 4, which is 5. Notice the i's disappeared. When you multiply two numbers that are the same numbers but different signs in front of the I part, they're called complex conjugates. When you multiply them together, the i's will cancel out. So we noticed on the last example that the answer was just real, had no imaginary part. They're the complex conjugate, which are the same numbers, just the opposite sign on the imaginary part. And when you multiply complex conjugates, the product is real. So to divide complex numbers, you multiply the numerator and denominator by the complex conjugate of the denominator. That'll remove the i's from the denominator, because we are not allowed to have any imaginary numbers in a denominator. So let's divide these. Notice the denominator is 1 plus I. The complex conjugate then would be 1 minus I. So we've multiplied both the top and bottom by the complex conjugate of the bottom. Multiply those. Wow, looks like a mess. Alright, so on the top, first, 2 times 1. Outers, negative 2i. Inners, negative 7i. Last, 7i squared. That's the top. The bottom, we have first, be 1. Outers is negative I. Inners are I. And last are negative I squared. So then we can combine like terms. That becomes negative 9i. I squared becomes negative 1. These i's cancel out, and that I squared becomes negative 1. And so that's negative 7. 2 and negative 7 is negative 5. Remember the form was a plus bi. So we need to split this up into two separate fractions. like that. We've now added and subtracted, multiplied and divided complex numbers. We have absolute values next. Absolute value is the distance a number is from the origin. When we're on a number line, that just made it positive, which is the distance from 0. Well, we're in a complex plane now, so it's not just a straight counting. So our absolute value of a plus bi would go over a and up bi. This is the distance from the origin. So that distance is from the Pythagorean theorem. It's a squared plus b squared equals c squared. So to get just the z by itself, we square root, so we have a squared and b squared. Notice in our formula, I is not there. I just means that we go in the I direction. We're not using it to find the absolute value. It's just the square root of a squared plus b squared. So let's find the square root of 2 minus 4i. It's the square root of 2 squared, because that's the a, plus negative 4 squared, because that's the b. Don't put an I. That's 4 and 16, which is square root of 20. 20 is 4 times 5, so square root of 4 times square root of 5. Square root of 4 is 2, so it's 2 times the square root of 5. An application of complex numbers is an art. It's called the Mandelbrot Set. It's a fractal picture created using complex numbers. In the following pictures, there's actually going to be an animation. The black part is the Mandelbrot set. The colored part is based on the number of iterations before the absolute value of that coordinate becomes greater than the square root of 5. I'm not going to go into exactly how you calculate the Mandelbrot set. It's just cool looking. So we're zooming in. Notice as we zoom in, you see the same thing over and over again. Oh, look, there's the set again. And zoom in further. Oh, look at that. That's cool. Oh, look, there's the Mandelbrot set again. Hey, it's repeating, just different colors. Oh, that's different. Isn't that cool? So what that's made is we started with a graph of all the complex numbers, and we graphed them all and colored them based on how that coordinate works on the formula. I use its absolute values, and we just zoomed in, so I got more and more decimal places. Let's finish by solving a quadratic equation. X is just there once, and it's squared. So let's solve by just taking square roots. Add the 8 to both sides, and then take a square root. Don't forget the plus and minus. So, square root of negative 28. Well, 28 is 4 times 7. So we could rewrite it as the square root of 4 times the square root of 7 times the square root of negative 1. Square root of 4 is 2, and the square root of negative 1 is I. So it's plus and minus 2 square root of 7 I. And that's it for today. Have a good day.